This work? Yay! Welcome to EECS 16A. Great to be here. I know for many of you, this is probably your first semester at Berkeley. Maybe you're here as a freshman, maybe you're transferring here from another institution. I want you all to know that we're thrilled you chose Berkeley, and it's amazing that you're here. We're really excited, and we're going to do our best to give you the best experience you can possibly have, hopefully starting with your first semester. There's a huge team of us, not just part of this class, but at the university, at the department, that are working super hard to make sure that you can have the best possible Berkeley experience you have. So I'm really thrilled to have you here. Congratulations, and give yourselves a hand. This is the first lecture. We're going to be here in Zellerbach today, as well as the next class, after which we will be transitioning to Wheeler Hall. This is probably the largest offering of 16A that we have had to date. We're going to have about 1,100 of you enrolled. Hopefully everyone who was on the wait list can get in, and we will do our best to make this class not seem like it is 1,100 people, but try to get to know as many of you as we possibly can. So for the first lecture today, we're going to spend a little bit of time, for you to get to know all of us and the teaching staff. We'll talk about some little bits of administrivia, the homework, so on and so forth, but you can all go read the webpage, and I don't want to dwell too much on these kinds of details. Really what I want to spend the large majority of this lecture on is talking about what we're going to be learning about in 16A, and why I think 16A, 16B are really a great introduction and a great way for you to find your place within the electrical engineering and computer science community. The goal of this class is to expose you to a wide variety of ideas so that you can figure out what parts of it you really enjoy and what parts of it you don't. And I'll give you more details about the class as we go along. But I wanted to introduce myself first. My name is Gireeja Ranade, and I am one of the two main instructors for this class. I will be co-teaching with Professor Bernhard Boser, who is here.
Hello.
Let me introduce myself, and I'll ask, he can also introduce himself. So I'm actually a Berkeley alum. I got my PhD right here at Berkeley. I wish I was also an undergrad here, but I sadly did not have that chance. I was an undergrad at MIT, so I spent time in Boston. And before that, I actually spent most of my high school years in India. I grew up there. Before starting on the faculty at Berkeley, I spent a couple of years at Microsoft Research up in Seattle, and I think Seattle is just one of the most beautiful cities that I've ever lived in. If you haven't ever had a chance to go there, I really recommend it. The mountains are something else. So I will be teaching Module 1 and Module 3 in this class. My research interests lie around control theory, information theory. I really like probability and applied math. I like modeling things. A lot of the types of control problems that I enjoy thinking about, you will learn more about in 16B, which is the class that follows 16A. You'll see hints of it here, but really some of the questions that arise when you're trying to think about data-driven models in robotics, these are the kinds of things that I like to focus on in my research. So I will be talking about, the systems part of the course. Largely, I'll be teaching Module 1 and Module 3, but of course, we'll be interleaving between and across the modules. I'll let Professor Boser also introduce himself, just to give so that you all can get to know him as well.
Okay, thank you. So, yeah, my name is Bernhard Boser. I didn't grow up in this country. I come from Europe, Switzerland. It's very beautiful there too. I recommend it. I got my degree at the ETH, and after that got a doctorate at the junior university across the bay. Just check their logo. It says junior, Leland, something junior. After that, I went to Bell Laboratories, and we will hear that word Bell today, actually. And after that, I came here, and I've been here for almost 30 years. I do engineering. I love it. I hope you will love it too, especially after taking 16. And I will, as Gireeja already said, I will tell you about circuits and what you can do with them and how you can coax them into doing what you want them to do. And I will also give you some examples from my research, which are on the fringe between mechanical and electrical. I make little mechanical things that can sense motion or fingerprints and things like that. All right, so thank you.
Great. So both of us will be up here lecturing, one of us or the other. But I encourage all of you to come to our office hours to get to know us in a little bit more of a smaller setting. It's hard to get to know everyone's names, it's hard for you to get to know us, but I will be having office hours almost every day right after lecture. Today I will have office hours right after lecture is over. And I encourage you to, walk with me from here to the room where we have office hours. You don't always have to have a technical question to come to office hours. You're welcome to come just to ask about Berkeley, just to try and get to know us more. And we're going to have a series of programs throughout the semester for you to get to know us as well as the rest of the teaching staff. Which is where I want to move to now. I want to introduce you to two very important people. These are your head GSIs. We have Sam and Sarika. And I'll let them introduce themselves.
All right, hello. It's on? All right. Hello, everybody. Everyone excited for 16A? Yes? Yeah, okay. All right. Everyone in the front is excited, and no one in the back is excited, which is sad. I'm excited about E16A. Sarika's excited. We have a large core staff here at 16A. We have 37 TAs this year. We're all here to help you. Our entire core staff is about 100 strong. So anything you need, we're here for. It's going to be a good and fun and exciting semester. We're going to talk about some administrative details to start. But
Go for it.
I just want to let everyone know, I mentioned we have a very large staff. As Ranade mentioned, we have a very large staff. All of us are available to you guys at any time. If anyone is struggling with class, if you guys want someone to talk to, come to office hours. Email any one of us. You're going to meet some of our core staff today. You're going to meet them in discussions, in labs, in office hours, which I highly encourage you to come to. It's a great resource. We have homework party, lots of great resources for you guys to come to and meet us in, because we get very lonely in office hours, and we want you to be there. So,
great.
Good semester.
Hey. Do you want the next slide, or good? No.
This is fine.
Okay.
Hi, my name is Sarika. I'm the other head TA. If you want to contact me, then please email eleng16a@gmail, or it should be berkeley.edu, actually.
Oh.
But this should also work. So before we move on, I have a few administrative announcements. So first of all, if you are in DSP, please send your letters to us as soon as possible to the staff email, which is, again, eleng16a@berkeley.edu. So send that to us as soon as possible, preferably like now. And so the other announcement is, so we do not offer alternate exam times. So if you have an exam conflict, then please try to work it out with your other course. And if there are any serious conflicts, then please let us know. Okay. So now we're going to introduce the rest of the TA staff.
Yes, let us move into introducing the rest of TA. I just wanted to have a little bit of logistics. So 3 things that you should all know in terms of this logistics. First, make sure you all know where the course website is. You should be able to access it, all kinds of details, homework solutions, lab, discussion sheets, everything will be posted here. Make sure you have access to Piazza. Make sure you also have access to Gradescope. And we'll be talking more about this, in the time to come. We are going to introduce the core staff, but I wanted to just also make sure that let me just check one thing, sorry. Sorry, next slide. Sorry, my slides were on order. Okay. Yes, great. Okay, so let us move on to introducing us, the rest of the course staff. Come on up. This is a group of people that have been working really hard already for the past few weeks to get the course up and running. And one of the things that I'm really excited about in terms of the people that we have here is that they're all here, and each one of these people cares about your learning, and each one of these people is interested in different things. And part of this is by design. We really enjoy having diverse personalities and diverse interests on our course staff because, you know, each one of the students is a different personality. You have different interests. I don't expect all of you to be interested in the exact same thing that I'm interested in, but hopefully you will be interested in something that one of these folks is interested in. And the idea is that by talking to as many different TAs as you can throughout the course of the semester, hopefully you'll get to learn different things about different research areas, different classes, and find your way through the Berkeley curriculum. So quickly, why don't you guys go ahead and just introduce yourselves.
Hi everyone, my name is Michelle, and my main technical interest lies in autonomous vehicle technology.
Hi everyone, my name is Michael Kalman. I research how to design microscopes better with artificial intelligence, and you'll see me at Thursday homework parties.
I'm Sarika again, and I'm interested in analog design.
Hi everyone, my name is Deepshika, and I'm interested in digital signal processing.
Hi everyone, my name is Craig. My research interests are in building autonomous insect-scale microrobots.
Hi everyone, my name is Panos Zarkos, and I'm interested mainly in integrated circuits for biomedical sensing.
Hello, my name is Christos, and I'm interested in integrated circuits for detecting cancer biomarkers.
Hi, my name is Jessie, and I'm super interested in embedded systems, specifically in aerospace.
Hi, my name is Miyuki, and I'm interested in mechanical design and dynamic modeling.
Hi, my name is Jinshu, and I'm interested in signal processing and control theory.
Hi, my name is Anika, and I'm interested in control theory as well.
Hi, my name is Amanda, and I'm interested in circuit design.
Hi, my name is Moses. I'm interested in control theory and communications.
Hi, my name is Ryan. I'm interested in semiconductor devices.
Hi, my name is Rahul, and I'm also interested in control theory.
Hi, my name is Grace. I'm interested in AI, specifically reinforcement learning.
Hi, my name is Alice, and I'm interested in how to make computing more energy efficient.
Great. Well, you guys are going to get to know all of these fabulous people much more over the course of the semester. Go to discussion. You will never find people who will care more about how you're going to do in this class. They are people that put in extra hours semester after semester. They come back with feedback saying, hey, by the way, I think something was unclear in lecture. Let's try this different strategy of teaching it in discussion. Let's try and improve the course for the next semester. So these folks really care. They're not here to judge you. None of us are going to try and say, oh, wait, are we sure these people were people to let in? We're here to make sure that you can have the best learning experience you possibly can have. We're here to show you our interests and learn about yours. Come to them if you have questions, if you need help. We're here to help. There's a lot of us. This is only a fraction of the course staff. You'll get to meet the rest as time goes on. But thank you very much, and we'll move on with the rest of the lecture. Thanks, everyone. In addition to all of these, we have basically a bunch of academic student employees. These are folks that will be helping you in office hours as well as in labs. They'll be also helping us grade all of your exams and all of your homeworks. So there's, a path for you to become part of the course staff as well, and I hope that many of you will join. And starting out is basically to become an ASC, join the TA staff, and move up this ladder so that you can actually, join this community. And hopefully all of you will enjoy doing this. Maybe some of you will even be here in my shoes one day. We have a lot of different discussion sections. Discussion is a very critical element of this class, especially given the course size. this is our chance to get to know you in a little bit of a smaller setting. This is on the course website. I don't expect you to look at this right now, but we have different groups of discussions targeted to different audiences in this class. Given that there's so many of you, I know that everyone is coming from a different background. Some of you took some courses, others of you took other courses, and we're trying to make it so that people can be in groups of people that are having the same learning goals that they are. So we have some courses, some sections, for example, that are targeted for freshmen, other sections that are targeted for transfer students, other sections that are targeted towards people who maybe have had some linear algebra experience. Just to make it clear, we don't expect you to have any linear algebra experience. This class is taught assuming you have never seen linear algebra before. But just because people come from different backgrounds, especially people who might be transferring, you might have seen some of this material before, you're welcome to go to one of these sections. There's a lot more categories. Please read the website. Choose whichever discussion you would like to go to. Find the one that works for you. There's different personalities, different types of teaching styles. Pick what works for you. Just make sure you go to one of them. The final and basically most important part of this class is all of you. Who is our target audience? We want to have a great experience for you, and really we're focusing on having this be a class. The style of teaching of the class is geared towards freshmen as well as incoming junior transfers. There's also a bunch of sophomores that are probably taking this class, and we understand that for some reason or the other you probably couldn't take it your first year, so welcome. Again, I want to emphasize we're not going to assume any kind of prior experience in linear algebra or physics. So don't worry about any of that. Some minor logistical things. There's going to be weekly homeworks. Homeworks will be due Friday at midnight typically. There's an exception of homework 0, which was released yesterday. This is a really simple homework. It's just about getting you familiarized with the homework submission process, getting you familiarized with Gradescope. So please make sure that you do it. It is due this Wednesday. This will be a graded homework, and it's really easy. So make sure you don't miss out on these points. There's more details about how to submit the homework and about resubmissions and so on and so forth on the website. I encourage you to go and read all of this. Gradescope will be the main technical or interface that we will use for submitting homeworks. Sometimes it can be a little bit complicated to figure out. One of the things that sometimes students have challenges with is figuring out how to select pages for your homework. So please remember to do this. We'll remind you about it in discussion. I'll post these slides later so you can also look through this. Little bit more administrivia before we can get into the real material that we want to get to. So let's talk about what our course policies are at some high level. Most of our stuff is on the website. I'm sure you can go read it, and I don't want to go here line by line through all of this with you. I trust that you will all go and read all of this and know all of this information. Our main goal in this class is learning. We want to help you learn something that you don't already know. And learning is hard sometimes. So please come to us when you need help. And a lot of the fact that we have homework, the fact that we have lab, the fact that we have discussion, these are designed to help you learn and get better. Our grading is absolute. There's no scale. There's no curve. So that means that you're not competing against each other. So we encourage you to collaborate, work together, and really also make friends in this class. This semester, we're going to be organizing a couple of roundtable events. So this is a chance for people to sign up to meet one of the professors in a smaller setting. We will be releasing signups for this in the coming weeks, so stay tuned for that. There'll be more information on Piazza. Okay, so what is our goal here? The one thing I want to talk about a little bit is course culture. And we're trying really hard to have a very positive and fun learning environment. And I really want to encourage you in this to collaborate and help each other out. And what we really, really want to discourage is a kind of competitive atmosphere here. We're really not going to tolerate people making fun of other people or being judgmental. college is a hard experience. A lot of the material that you're going to be learning, it will be very fun, but it might not be easy. You'll have to work hard at it. And we're going to rely on you to, work together to kind of build and get better at this. There's a lot of tips on, how you can succeed in 16A. Most importantly, make sure you get enough sleep. I don't want to go through too many of these details, but think about it. I'll post these slides later, and make sure that you can, follow along. So with that, I really want to, get started with the technical part of today. I don't want to spend too much time on any more administrative details. So I'll start with a question. Do you know what is the key idea that is used to allow touch screens to detect touch on, let's say, your tablet or your iPhone? What is this idea? What is maybe the idea that allows an autonomous car, some people here were interested in autonomous cars, to drive in a straight line? The same idea turns out to be useful for letting search engines rank web pages. It is also a key idea in training neural networks, which maybe some of you have heard about. Any ideas on what this might be? Yeah? Yeah, you. Linear algebra is a big part of it, but even more specifically, the specific part is eigenvalues and feedback and stability. And these are some of the key ideas that we're going to be learning about in this class. And eigenvalues and feedback stability, these ideas are actually so important. I recently found out this summer that they're also incredibly important for time travel. You maybe saw this. I talked to Marvel over the summer. I told them I was teaching this class, so.
Run one last sim before we pack it in for the night. This time in the shape of a Mobius strip. Invert it, please.
Processing.
Right, give me that eigenvalue of that particle factoring in spectral decomp. That'll take a second.
Just a moment.
And don't worry if it doesn't pan out. I'm just kind of...
Model rendered.
Anyway, so eigenvalues, as you can see, are very, very important. Spectral decomposition, we'll talk a little bit about it in this class, but if you really want to learn what singular values are, you'll have to wait till 16B. And then there's all of quantum physics, which you'll have to go to another class for. But soon enough, we'll get there. It's actually interesting. Avengers seems to be connected with this class ever since the beginning. This was a picture that was made by the first ever cohort that took 16A. This was the pilot back in 2015. And it seems like the movie has grown up with the class, and we hope to keep the theme running. So I'd be curious to see what you folks come up with. But moving from movies to our scheduled programming, let's think about another thing. What's the key idea that makes Shazam work, and it also makes the GPS on your phone work? Another idea that we will be learning about in this class. I don't expect you to know it because we haven't taught the class yet. But by the end of the class, you will know exactly what this is. And this idea turns out to be, oh, is there a suggestion back there? No? Fourier transformations are very related, but we actually don't even need to use Fourier transformations to understand this. We can understand this at a simple level using the idea of cross-correlation. Fourier transforms are something, again, that you will learn more about in 16B. Cross-correlation will start out with right in 16A. And finally, one more thing we're going to be talking about. A fundamental algorithm in machine learning and AI, and it's used basically at this point every single day to make predictions in biology, and brain-machine interfaces, in social science, imaging algorithms, all kinds of things. What's this algorithm that we're going to be learning at the end of 16A? Yeah? Regression, least squares. So by the end of this class, I don't expect any of you to have any idea of the answers of this right now, but by the end of this class, I hope that you'll be able to go and tell your younger siblings and your younger friends about all of these cool things. Because it's up to you to inspire the next generation of folks to, join STEM majors and be part of this community. So hopefully you can share this message. So just to give you a little bit more detail about what we're going to go into in this class and how are we going to cover all of these different topics. 16A is not a survey class. I know some of you might have heard that, but really what we're trying to do is we're trying to give you a rigorous foundation, not just for the next 4 years of your time here at Berkeley, but for the next 40 years of your career. We're not just trying to prepare you to solve a problem set or get your first job interview. We're trying to prepare you to learn on your own as you go ahead, technology changes, and you have to deal with real-world challenges, things that are unspecified and things that might be very dynamic and unclear. And which is why this class is structured the way it is. So the first module is going to be an introduction to systems. And here, we're really going to try and learn how do we build a model? How do we take something abstract and unstructured and put it into a mathematical formulation that we can build on and work with? The second module is the really powerful part where you say, well, I have a model. That's great. I can do a lot of analysis, right? Iron Man could do a lot of analysis, but if he couldn't take that analysis and go the next step to actually design what he needed, that analysis isn't good for anything. So module 2 focuses on design. How do we use these models? And how do we actually build things in the real world that get us what we want? So here we'll be starting to introduce circuits so that we can take the models that we have for circuits and use them to build different things that we would like to build, and particularly focusing on touchscreens. And the third module is going to be talking about learning from data. So if we wanted to learn about the real world, if we wanted to learn these models instead of just guessing what they are, how do we do that? And we'll talk about the basics of machine learning. 16B picks up from here and gives you a lot of the aha moments that 16A is building up for. So there you'll talk about advanced circuit design, you'll talk about an introduction to robotics, and you'll also talk about an introduction to what is called unsupervised learning that we'll talk more about later in this class. So the two main goals in 16A and 16B are really to introduce you to these ideas of modeling and problem formulation, and this will be happening in Module 1, and design thinking in Module 2. And kind of the third module is putting it all together. We're going to see different kinds of conceptual tools through linear algebra, and the circuits module is going to help us really take these modeling tools to implement and build things in the real world. And the idea is that this will give you a sense of, the different kinds of things you can do within the EECS department. And there's many, many different things you can do. So for example, if you get really interested in the algorithms part of this, well, maybe then you will end up taking classes like optimization and AI and machine learning. But if you're really interested in how to design a medical device, how do I build a Fitbit? How do I build a better ICU monitor? Then maybe you'll take classes like 105 and 140. Maybe you'll get really interested in energy, and you'll think about how to design better solar cells. And then maybe you'll take classes like the 130 series. Maybe you'll be interested in larger scale design, maybe in human factors, maybe large scale networks, maybe hardware design. And then there's a series of hardware classes. Or maybe, you'll take the 16B final project, you'll think the robotics car is so cool, and you will want to take the series of robotics classes that we have, like 106 and 149 and 128. So the goal in 16A, the reason that we expose you to many, many different types of things is that, you know, all of us believe, and I personally believe, that there is a spot in this department for each one of you, and we want to help you find it. You know, you're not expected to like and enjoy every single homework problem or every single class that you take. You just have to like the few things. So please go ahead and try to figure out what that is. So with this, I'm going to actually pass over to Professor Boser to talk a little bit more about the arc of this class.
Thank you. If you were born 150 years ago, this is how your smartphone would look like. You may laugh about this now, because heck, I mean, how does this look like a smartphone? Not very much. Huh? But maybe 150 years or even less than that, other people, others, or maybe even we, will laugh about what today we consider a smartphone. And who is gonna invent and create this new reality of smartphone plus plus? I don't know how it's gonna look like. Well, it's you. Engineers and scientists, and you obviously chose to become engineers or scientists. So 16 is gonna help you to transform something like this into whatever your innovation, the next generation. Okay, so how is this smartphone? Just very quickly, there is a key where you can send sort of like smoke signals, but electrical smoke signals of various durations. And with that, you can encode messages. For example, what weather it is or so, or a greeting. This was very revolutionary at the time, and people managed to communicate farther and farther where smoke signals, for example, wouldn't work because there was no line of sight. And ultimately, somebody had an idea, gee, you know, maybe we could link continents together, Europe and America. And so they put the cable at the bottom of the Atlantic Ocean, and they thought, well, now we will let these electrical pulses travel on this cable. Well, it worked just long enough for the Queen of England to send a greeting to the President of the United States, and then it stopped working. That wasn't a plan. They planned, just like today, that this would be a revolution. And they didn't know why it didn't work. So they looked at it, they analyzed it, where did it break? And ultimately, they figured out more and more, and they could make reliable communication. They also, along the way, changed the way. This was electrical. Now we do it more likely optically. But that's what engineers do. They come up with a great idea, they implement it, and sometimes it just works. But guess what? Most of the time, it doesn't. And then engineers or scientists go and figure out what's really going on. They create models that can be used next time when they innovate something new that builds on what they came up before. A few years later, then Alexander Bell, he came up with an idea where you could send voice signals through such wires. I worked for him, but he didn't know it because I came a little bit too late. Okay, so we moved from what was on the previous slide to what is on this slide. This actually has changed a little bit. We moved to this. So how did we get there? Well, so first of all, this is very different from what sort of an original, let's say, Morse key can do, because this not only can communicate, it can also sense the environment, it can figure out what's going on. It can think about the environment, drive a less car, for example. It can decide what actions to take, for example, to accelerate or stop or turn. And it then can actuate, accelerate or stop or turn. So how do we build stuff like that? Well, what is the fundamental technology that we use for this? Well, the key technology that sort of is at the basis of all of this is silicon integrated circuit technology. And in particular, there's a component that incidentally was invented at the Bell Laboratories of that guy, that guy Bell found it, and it's named after him. The key component is something called a transistor. Well, what's a transistor? Well, a transistor essentially is a switch, just like a light switch, except it has a few differences. One very important thing, just like the light switch, it does let electrical current flow or not, and we'll talk about what electrical current is later also, but it doesn't use a mechanical action to do that. It uses another electrical signal. And because it uses an electrical signal, it produces an electrical signal, you can cascade those, and if you cascade many of them, you can do incredible stuff, like a smartphone or a computer or so. The incredible thing is that we have managed to put more and more of these transistors on a chip. It started with just one in the 60s or so, and then this number exploded. Now, the chips with the highest number of transistors is over 1 trillion transistors. So in your pocket, you may be carrying a couple of chips, a few trillion transistors. This incredible growth of the number of transistors, which, by the way, continues, was predicted by a fellow, Gordon Moore, who was an alumni from UC Berkeley. He, in the 70s, or even late 60s, he realized that the number of these transistors that they could make on a single chip. What is a chip? Well, it's a sliver of silicon, a very common element on Earth. We're not going to run out of that. How many transistors they could make on a chip was increasing every year. And it was very important because he was a co-founder of Intel, and Intel absolutely depends on being able to make more and more of these transistors because it makes more and more powerful computers. So it started with just a few, and then he captures this observation, saying, you know, it doubles. The number of transistors we can make on a chip doubles about every 2 years. Imagine that. Go get a job when you graduate from here where your salary doubles every 2 years. You will do very well. You will do very well. Anyways, okay. So how is it possible to put more and more stuff? Well, one way would be to make it bigger and bigger, and of course that's not what we did, right? So here, that's all. Mark Bohr is also somebody from Intel, a fellow from Intel. He is 1.60 meters tall, and he put together this chart illustrating how small transistors have gotten. So a fly, 7 millimeters, already pretty small compared to Mark or you. A mite, even smaller. Actually, what's the diameter of a hair? A human hair? Well, about 1/3 of a mite. So a mite is still big compared to a hair. A blood cell, a few micron. A virus, 100 nanometers. Who has seen a virus? You have a very good microscope. Right. So transistors are even smaller than that. Actually, when I was, my senior thesis was building a chip, and the transistors that I used, they were 7 micron long, 7 micrometer long. So still very small compared to a hair. I had to use a microscope to see them. Well, now they're 1,000 times shorter, 1,000 times. So that means you can put 1,000 square, because you can put them in X and Y, 1,000 times square, 1,000,000 times more transistors on a chip than I could when I was a student. Today is an absolutely incredible time, because things have changed dramatically for you than they were when I was an undergraduate student. When I was an undergraduate student, we had all sorts of ideas. We want to do this or that, and we want to build a computer that we could carry around. We couldn't. It was way too big. Because the technology was simply not powerful enough. We couldn't do that. Today, it's different. The technology is incredibly powerful, almost infinitely powerful. And what the opportunity this gives you is that you can have an idea. If you have a good idea, you probably, with your engineering and scientists, scientific knowledge, you will be able to implement it, and you can create something new, something great new. Okay, so that size. So you will notice here, transistors today are a few nanometers. The silicon atom is about 1/4 of a nanometer, so we are going to get into some difficulty here, but there are ways around it. For example, we can put in 3 dimensions or so. Anyways, the technology, the power of technology has been increasing and continuously increasing incredibly, and now more and more it's a question of where is that killer idea? What are we going to do with it? Okay, so of course if you build a system where just one chip has 1 trillion components, then you need to be a bit organized about it, right? You can't have in your notebook 1 page for every transistor. That notebook would be a little bit too big. So we need some way on how to do that. And there are a number of powerful things. Usually they're called abstractions that help us to deal with such complexity. And here are pictures of 3 people that contributed very significantly to developing the kinds of abstractions that we use as engineers to build unbelievably complex stuff. The first one, Ada, she had an idea which at the time, now this is sort of common sense, but at the time was totally revolutionary. She wrote an algorithm, sort of a set of instructions for a machine to execute. And if you think about it, that's precisely what a computer program is. So she was the first computer programmer. Then Alan Turing, a little bit later, about 50 or so years later, he asked the question. He did lots of incredible things, but one thing that he asked is the question, well, what is it really a computer? What are really the essential elements for a computer? If you think about it, the computer that you carry around, your smartphone, your laptop or so, are unbelievably complicated things, and in order to think about them, it's not very helpful to have something very complicated to try to figure out what it's doing. So Turing figured out a very abstract, very simple kind of thing that captures all the essence of a computer. And it's called the Turing machine. You can look it up on the web, how it is. It's a sort of a tape. It's very simple. But now, because this is so simple, yet it describes all that computers possibly can do. Simple, but complete. It allows us to figure out or answer very fundamental questions. For example, and you may have thought about that in an exam or so sometimes, when you ask a question, and in an exam you want your answer, right? But there is another question you can ask. Does this question even have an answer? Is it even possible to answer this question? And hopefully our questions in our exams, they all will be answerable. But it's interesting to realize that not all questions do have an answer. Questions that seemingly should obviously have an answer, they do not always have an answer. And using these abstractions that Turing came up with, we can on a very profound sort of mathematical way, we can figure out whether a question has an answer or perhaps not. Claude Shannon, he came up with a lot of profound theories. Sort of a side thing that he did was he came up with the theories that said, well, if you have switches, remember, they were not transistors when he invented that, but now they're transistors. If you have switches, then you can do computation with them. And his master's thesis showed that out of just switches, total revolution at the time, you can make an adder. You can make a lot more things with them, but he showed that. And he showed also other very important things. For example, you want your smartphone to communicate faster and faster and faster, right? To download these websites almost instantaneously. Well, why is it not instantaneous? Huh? why don't we just make it infinitely fast? Well, there must be reasons. And in fact, there are very fundamental reasons why we can't make things infinitely fast, and even more profound, there are exact explanations how fast we can make a communication. Okay? So Claude Shannon came up with a number of theories that allow us to answer questions like that. If you have these and these constraints and parameters, then you can communicate at this rate at most. Okay, so how this relate to 16A and then ultimately 16B? Well, this is sort of a very general, and I guess that's the point here, a very generic picture of what these courses are. In 16A, we will learn how to use technology to sense the environment, and then how to act on the data that comes out of these sensors and think about them using computer algorithms. Okay. 16B then adds to that and, a module of actuation. Now that we've thought about it, we want to do something with it. A good example for this would be a driverless car. Hopefully it senses something. Oh, there is a pedestrian, I better don't move. Okay. Or there is a turn, I better go left. It processes a wicked big computer, more than 1 trillion transistors probably, that processes all this data that comes from cameras, like that you will be building in the lab here, and other sensors also. Uses algorithms like, for example, these learning algorithms that you will be hear about in this course. And then, of course, it uses actuators, engine, steering wheel, and so on. Another thing that you may recognize from this slide is that this is not just about sensing and hardware and sort of the engineering part. It's just as much about algorithms and computer algorithms and computer programs. Okay. So in this course, we kind of will balance back and forth between hardware, physical things, and more abstract things, algorithms and computer programs, because we need the combination of these two in order to make all the things that we want to construct. Okay, so here are a few examples that you will see throughout the course and also in the laboratories. You will build an imager. How does your smartphone take a picture, right? Oh, you press the button, yeah, but what's actually going on there? So you'll build one. And there will be devices inside that do this. There will be physics, and then afterwards there will be processing matrices, linear equations, and so on that think about what came out of these sensors and render an image, like EE16A. There should be EECS 16A. We have to change the slide. Touch screens. How come when you just slide your fingers on the screen of your smartphone, how come that smartphone figures that out? Well, same story. There are circuits that detect your finger using crazy stuff like capacitance. We'll talk about that. And then there is processing elements that figure out what these signals are doing and what your intention is. Positioning, you heard about GPS. Well, GPS uses electromagnetic waves in order to figure out how far we are from a few satellites. Electromagnetic waves are kind of hard to see. Can you see them? Actually, you do. You're seeing me. I'm just an electromagnetic wave, and so are you. But anyways, we are going to use sound in that laboratory in order to localize everything. Okay? So just one last little thing, so that I told you that I love engineering. I like to work sort of on this fringe between physical and algorithms. And this thing here is a gyroscope. Under that can is a thing that wiggles just a little bit. In fact, it wiggles sub-nanometers, very little. And then we use fancy electronic circuits to detect that wiggling. And you can't see this, but on the other side of this called the printed circuit board, there is a chip an ARM processor, a CPU, a little computer, and 10,000 lines of code, and it figures out what these wiggles mean in terms of motion, so we can detect how this thing is moving around using these algorithms. So you will learn in this class how to do this, how to take something physical, extract signals from the environment, and then how to use an algorithm to get interesting data and solve problems with that. Okay. Thank you.
Okay, so this gives you a little bit of an overview of what you're going to see throughout this class. And now it's time to, get started with Module 1. And Module 1 is going to be talking about imaging. So this is a picture from 1632. It's actually a painting by Rembrandt, one of his most famous. And what they're showing is it's a group of doctors and medical students trying to examine the inside of this man's arm. They're trying to learn anatomy. And if you wanted to image, or if you wanted to see what was going on inside someone's body, if you went to the doctor and you said, well, my stomach hurts, what would the doctor do? The doctor would say, well, let me make a hole in you and see what I can see. Maybe I'll find what's wrong. I don't think that modern medicine would have gotten to where it is if we had continued this kind of process. And what we can do today, of course, is something that is much more powerful. If a doctor wanted to see what was happening inside of you, under very rare circumstances, would they actually try and physically cut you open? The first pass would probably be something like either an MRI, magnetic resonance imaging, or taking an X-ray, or a CT scan, or trying an ultrasound. These are the new ways of seeing inside our bodies without doing any kind of surgery. And these are all examples of what we call tomography. And that's going to be basically the foundation of the first module. Every single one of these technologies has been built off of the fundamental principles of linear algebra and circuit design that we're going to be learning in this class. None of the medical technology would have been possible without it. So the very first lab, which is the imaging lab, is going to try and give you a sense of, well, how does tomography actually work? So let's really think about this, right? Let's assume that it is not desirable to slice open my brain. Maybe by the end of the semester, some of you will want to. I hope not, but you don't hate me yet. So how would tomography actually try to see inside what's going on? Tomography, this word actually comes, that means literally slice and write, to see basically, to see inside, try to understand inside what's the slice going on. And so how does tomography work? Well, let's say I wanted to take a picture of someone's brain. What tomography does actually is it takes measurements. It uses some kind of energy source and tries to understand how this energy source interacts with whatever it is trying to image. So let's say if you were trying to image your brain and you were trying to use an energy source, for example, if you were trying to use a magnetic field, this magnetic field interacts differently with different tissues and different parts of your body. So it interacts differently with the blood, it interacts differently with the tissue, with the muscle, with the bone. And these differential interactions are what can be used to actually image what's going on. So what you would do is you can take basically this energy source. In our class, we're going to be modeling this with light. I'm going to take this energy source and do a measurement. I'm going to basically shine it along the line, along whatever I want to measure, and take a measurement. These measurements are also called projections, and we'll talk more about this in this class. So one measurement typically isn't going to be enough. This one measurement will basically be, let's say, the sum of all of the different values along the particular line. And we'll make this more specific just in a minute. But instead of just taking one measurement, what tomography will do is it'll actually take many, many measurements. It'll take 1, 2, 3, many, from many different angles. These many measurements will then be combined using computation to give me the actual image that I'm trying to recover. The fundamental principle behind this is basically solving systems of linear equations. And the way we can do this is linear algebra. And that is what the first part of this course is going to be about. So what do each of these pixel values really represent, right? When we look at this picture, when the doctor looks at this picture, she knows how to interpret the different colors here to mean different things. She knows that a certain shade means maybe this is bone density, maybe this is a blood vessel, maybe this is tissue, so on and so forth. What we're trying to recover is the different values of the different pixels, right? They mean something to the expert that is interpreting the image, but we're engineers. We're just trying to figure out what these different pixel values are. And how can we solve and figure out every single pixel value in this image from just these measurements or just these projections? That's exactly what tomography is going to do. So this is a very high resolution image. There's lots of detail in here. And to get a higher resolution image, we need to take more and more measurements. But we're just starting out as an introductory class in EECS. So let's start with a simpler problem. And this is a theme that we're going to see coming up in this course over and over again. When a problem is complicated, we're going to try and simplify it so that we can understand what's going on. So instead of such a high resolution image, let's try to maybe make this even more and more low resolution. Let's say, this picture actually only had 4 pixels. And there were 4 different pixels that we were trying to understand. So I want to switch to the document camera to just do a little bit of a calculation. Okay. So what I want to do here is just try to think about how we can understand tomography in this very, very simple setting. Let's say I have an image, and it's represented by these 4 pixel values. X1, X2, X3, X4. And I want to take measurements, right? I want to be able to measure what's going on. So let's say what I'm going to do is I'm going to, let's say, shine a light source through this. And what I'm going to read out is, let's say, the amount of light that is absorbed. So I get a measurement out, B1. And maybe what you have is different types of tissues are going to absorb different amounts of energy. So if you have more energy absorbing tissues, you will have a smaller readout. If you have higher energy absorbing tissues, you'll have, if you have high energy absorption, you'll have a smaller readout. If you have low energy absorption, you'll have a high readout, right? So we're making a simple abstraction model. Let's say we can actually write this as a simple model. And whenever we put this light source through, or this energy source through, we get the following measurement out. We get x1 plus x2 is equal to b1, where x1 and x2 are our pixel values. Do you think that we can figure out all of the pixel values from this one measurement? Probably not, right? So let's take a second measurement. Let's say I take a second measurement, and here I get B2. And I get x3 plus x4 is equal to B2. I'm going to call this equation 1 and equation 2. And maybe I take another measurement here, and I get equation 3, which is x1 plus x3 is equal to B3. And I take another measurement, and I get 4 x2 plus x4 is equal to B4. So this is a setup. If you go and read the notes on the course website, what you'll see is that we are discussing a similar example in the context of a grocery store. And there the example is, let's say you are in a grocery store and you have a giant stack of, juice bottles or drink bottles. And you know how you have these crates that can be stacked on top of each other. And what you're trying to do is you're trying to figure out what are all of the juice bottles in all of the little entries. But you don't want to take all of the stack apart to recount everything. And so you want to use a technique like tomography. And let's say you knew that the juice bottles, or the bottles were either orange juice, or just water, or milk. Right? So you have this giant stack. And what you do is, let's say you shine a laser beam through. And you measure the light that remains on the other side. So what you have is you can see how much of the light is absorbed by the different bottles. And let's say you knew that a milk bottle absorbs a certain amount of light, and the juice bottle absorbs a certain amount of light, and the water absorbs another amount of light. What you can think about is writing this as a system of linear equations to then solve back and measure and figure out what every single one of the little bottles in that giant crate are. And the number of measurements that you would take would be what? If you had 4 unknowns, how many measurements would you be expecting to take? Probably 4, right? So in this little example that we have, here we're thinking if it is an image, you can go read the notes, which I highly recommend you do, where you can talk about it where you can see it discussed in the context of this grocery store. So here's a system with 4 equations and 4 unknowns. Many of you might have seen a similar system of equations before coming here. So why don't you just, take a minute and see if you can solve this. And I encourage you right now to turn to your right, turn to your left, and introduce yourselves to the person next to you. That way you're going to know at least one person in this class. Make sure that no one's left out. Look to your left and to your right, and be inclusive. Remember, we want to try and build a community. And as you're talking about yourselves, tell people your name, but then also think about how you would solve this problem here. So how many people are ready to start discussing this? How many people have some idea of what this system with 4 unknowns and 4 equations is like? Is there something funky about it as you try to solve it? What happens if you take equation 1 and equation 2 and add them together? And compare that with what happens when you take equation 3 and equation 4 and add them together. What do you get? B1 plus B2 should be equal to B3 plus B4. What's on the left? What is equation 1 plus equation 2? Equation 1 says x1 plus x2, and then we have x3 plus x4. So you have one side x1 plus x2 plus x3 plus x4 is something. And you also have x1 plus x2 plus x3 plus x4 is something else. Right? So what you have is you have 4 measurements. But are these 4 independent measurements? Can you recover the 4 pixels using this? Not quite, right? Those of you who tried to work it out, I encourage each of you to bring a piece of paper and a notebook to class, even if you're not taking notes, because we will have these little exercises to do, and it usually helps to have something that you can scribble on or doodle on to try and work things out on your own. But turns out that, we started out thinking, oh, 4 equations, 4 unknowns, we're going to be able to solve this. But turns out that this isn't actually going to work, right? So, okay, now you're the engineer in the room, and you're faced with a system. You had an idea, you tried it, we tried it, but it didn't work. What do? We're at the design part of the system, design part of the problem. How do we get around the roadblock? Take better measurements, right? Take better measurements. So take a minute, talk to the person on the other side of you who you have not yet talked to, and try and figure out what other measurement would you like to take. Make sure you don't leave people out. So do we have any ideas? Let's see if we can communicate without words. Can you show me making hand motions what you would want to do? Right, exactly. People are saying go diagonal. Go diagonal. So what if I gave you this? x1 plus x4, let's say, is equal to b5. So now you have equation 5, x1 plus x4 is equal to b5. Now can you solve this? Yes. How do you know that you can solve it? Maybe you can show and you can prove and you can solve it out by hand. And in this case, where we have 4 variables, and thankfully 10 fingers, we can actually solve this, right? Because we can count the number of variables, on our hands. But if you were to go to a doctor and the doctor was going to try and image your brain using only 4 pixels, would you go to the doctor again? So when you're actually trying to solve systems of linear equations in the real world, you're probably not going to end up in a situation where you have 4 variables. Quite likely, you're going to have hundreds or thousands or millions of variables. Probably that is not a calculation you would want to be doing out by hand, even if we had 1,000 people in the room together. the probability of getting that correct would be really, really low. It turns out that actually there were a lot of important calculations that used to be done entirely by hand, right? I mean, how many people in the room have seen the movie Hidden Figures? Right? I think it's a great movie, one of my favorite all-time movies. And you know, there you see that there were these large groups of people, mostly women, that did out large calculations by hand. This was way before computers, and these led to some of the key scientific advances that have brought us to where we are today. But today, in this day and age, we're past where we want to do calculations out by hand, right? We now have computers. And what we want to be able to do is systematically use our compute power to go beyond 4 equations and 4 unknowns to millions of equations and millions of unknowns. You don't want to have to solve out, 90% of your equations only to realize that, oh, I didn't take the right measurements. How can I just enter a stack of equations into my computer and have my computer tell me, hey, these are great measurements. You can solve them. Or, oh my God, you screwed up. You need to take better measurements because these are redundant or these are not solvable. This is exactly what we're going to try and learn in this class. How can we systematically solve large systems of linear equations? How can we design measurements so that we know from the get-go, before trying to solve, that our system is actually going to be solvable? We want to avoid the problem that we just ran into, right? We want to know that our measurements are going to be successful. And the principled way to do this is going to be through building up a lot of linear algebra. And that is the course of this class. So the key algorithm that I will be talking about next class and over the next few lectures will be basically this idea of Gaussian elimination that will help us know, when given a system of linear equations, how can we systematically know whether we have one solution, whether sometimes we might have infinitely many solutions, or whether we have no solutions at all. And we know how to do this by hand, but we're going to think about how can we think about this geometrically, and how can we do this while harnessing the power of compute, and while harnessing the fact that Moore's law has actually given us these incredibly powerful computers. So the first module will be talking basically about this, and we'll be talking about an imaging lab. If I can just have this show up again. Okay. So the first imaging lab is basically going to be talking about tomography. And we're going to be talking about tomography using a simple light source, and we're going to be talking about a single pixel camera. So we're not going to be using a multi-pixel fancy MRI machine, but how can you do this with just one sensor? So we'll learn more about this basically in the next class. I will talk a little bit more about the first lab, and then we'll start going into details about how we're going to solve these systems of linear equations and how we can do this systematically. That's it for today. Please make sure that you go and check out Homework 0, and I will see you here next week.